Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and this is lecture 26. And in today's lecture, we're going to be covering the logarithmic function. So, start off with our title for the day. We have lecture 26 and here is the logarithm. Excellent. Thank you for saying that you can hear me. Logarithmic function, and thank you for, of course, tuning in on YouTube. I saw we were having issues with Big Blue Button today, so at least this is working today for us. And it looks like it's a small group today, so again, since it's small, I guess people either know it already, and so they might not want to sit through something that they find very tedious. So no quiz. That's correct. We don't have a quiz this week. We have a test that we're prepping for this week. For sure. Okay. So last time we done the exponential function. So we, from last lecture, we had looked at functions of the form b to the x, and that's where we had this is our base. And this was our exponent. And those are what we called exponential functions. And that was, again, to differentiate it from, say, other functions that we had looked at previously when, we were looking at, say, x to the n, where x was our variable. So again, the base here is fixed and our exponent is variable. And in this case, these are what we'd call power functions. We also had like that power rule. Will this be on the test? No. I don't think that this will be on the test. It will be on the exam, but it won't. I don't think. We have a lot of material that we covered from test 1 to test 2. We've covered, curve sketching, again, is a great summary for what we had covered from test 1 all the way up to test 2. So curve sketching, optimization, that's a lot that test 2 will be covering. But logarithmic and exponential functions, we also have to do then the derivatives of these functions. So yes, we will eventually have to test this. This will show up on the final exam, but no, it won't show up for test 2. But it's a good question. Okay, so returning back to this, we have power functions, and this is the, in this case, this is the base. And this would be, okay, excellent. No, it's good. I like the questions. It's what I'm here for. And this is the variable. Is there somewhere where the steps for curve sketching are posted, or should I just go back and pause the last lecture? I'm not going to try to mangle your name. I'm just going to say Cameron. For Cameron, so on the assignment, the last assignment that I posted, I actually, I think item 2 goes through the 8 steps. So they're all listed. However, those are the steps that we had used for the curve sketching previously. So we had a domain an x-intercept, y-intercept, horizontal, vertical asymptotes, increasing, decreasing, local min-max, concavity, points of inflection, some additional points if necessary. But I wrote those out again in the assignment just in case. So I would suggest going to the assignment and looking at that. I think I might have even, and I have some like commentary or something for each step as well. So I hope that answers the question. Okay, excellent. Exponents, we have fixed. Okay. So I have this function, these exponential functions is what we're going to be looking at. So again, a lot of this is kind of like recalling from what we did. So this was from last lecture. We're also going to recall the inverse of a function. So an inverse of a function is that if well, let's see. The inverse of a function is if I have the inverse of a function and I pass in the range of that. Sorry, I'll say the inverse of x is equal to y. Then that is equal to the value that I get like this. So I'm not sure how I can explain it algebraically, but what I can do is I can show you a picture. So for instance, if I had something along the lines of I have two sets. I'm going to call them arbitrary sets. I'm going to have x and y, and I'm going to have a point here is x, and here's a point, and here is y. Then that means if I have this mapping, just according to this, if I have this mapping, here's f, it's mapping from mapping y to x. So this function takes y and maps it to x, and so I'll call this f. And what that inverse function says is that if I take x, it will map it back to y. So if I do that, this is my inverse function. Okay, so that means that if I wrote something out like, okay, now what I'll do is I'll write out, so we're talking about inverse functions. And so what I was going to get to is what is the inverse function of the exponential then? So we'll write it with some form of shorthand. So we'll say that the inverse function, so the inverse, so we have f to the, we have this -1. That's not like an exponent. It has a very specific meaning because, again, I have right -1. This is applied to a function that we mean that this is the inverse. So the inverse of the exponential function and we use the function f of x, b of x is called the logarithmic. Yes, it is the logarithmic function. Excellent. Good. And then I'm going to add with base b. Yes. But there's a lot of preamble. Like we talked about exponential functions, power functions. We talked about what an inverse was. So okay, and it is denoted by log base b. Okay. So again, I can look back up to this rule up here. So that is my inverse function. So what I'm going to say is that I'm going to just copy this rule out again. Okay, so that means that if I have my inverse function, which is the log base b of x, that's equal to y, then I have to think of my function, my exponential function. So in this case, I'm thinking of b to the x. But in this case, I'm actually putting y. So what they're saying is that I have to pass in this y. So it's b to the y. So just to kind of... So in this case, that I have b to the y is equal to x. So these are equivalent. So I could write it, the logarithm of b of x is equal to y is equivalent to b to the y equals x. Most of the time with an inverse function, what we do is, again, we're just swapping the domain for the range and the range for the domain. The other thing to note is that in this case here, if I did this function here, so if I did this, if I did f inverse, so I'm going to take this x, okay, which brings me to y, and then I apply f again, that equals x as well. So again, I apply an inverse function, and then I apply that function again, and it brings me back to the original spot. And the same thing can happen again if I did it with y. So again, if I did y, I have f of y, and that brings me to x, and then I apply this again, the inverse, that's going to give me y. So what you're seeing is that if you have the function and then the inverse of the function on the element, it's going to bring you back to the original element. So what does that mean? Okay, I'm going to write, I have the two rules then. So I have the inverse of f of x, that's equal to x, and then I'm also write it. Okay. So it follows from this that I'm going to use, so our inverse function is log, so I'm going to write the log of b of our original function, which will be b to the x, is equal to x. So that's true for all the reals. And if I change the order, so instead I have b to the x, so I have b, and in the x is going to be my log b to the of x. That's equal to x as well. Now that only holds for x is greater than 0. Okay, so we kind of understand now algebraically that we have an inverse of a function. But what does that mean in terms of the graph? The graph of the inverse, or the graph of the logarithm, is obtained by reflecting the graph of the exponential in y equals x. Okay, so maybe I'll write that out so that the graph of that function is obtained by reflecting the graph of the original function, which is our exponential function, in y equals x. So let's see how well I do this. Okay, maybe what I should do is we'll do, there we go, something like that. So this is b to the x. And then I said we're going to reflect in y equals x. So it's just a diagonal line. Kind of wish I had some, I don't have them here anymore, but we used to have like a mirror or a lens that we would put there, and you would have the original drawing, and then you would have an image on the other side of the lens. No colored. Oh, okay. He wants colored pens. Do you know what? No colored pens. Well, I will fix that. I will fix that. I will make everyone happy. Everyone wants color. Okay. So in this case, I have 1, 0. So right here is 0, 1. And I'm going to try to reflect that. So it should look something like that. So this will be y equals log of b x. So I'll keep using this pen for the logarithm, but on this side, just as a reminder or a recall of what we had done last time, we know that the domain for the exponential function is from -infinity to infinity. We know that the range, because this is a horizontal asymptote here, it never, and as it goes to infinity, it's going to go to 0. It actually is bounded below by that. So that range is from 0 to infinity. We also have a horizontal asymptote, which I mentioned. Horizontal asymptote. And that is y equals 0. We also have that y-intercept, which is 1, 0. And do we have an x-intercept? No, there is none. No x-intercept. So, sir, did you label those points? I probably did. Yes. Thank you. Thank you, thank you, thank you. Yes. X-axis should be 0. Here's 1. Did I just draw it and say it again? No. It should be 1. X is 1. There we go. X is 0. There should be 1. There. Perfect. Now it's all good. Excellent. Thank you. So again, it's a reflection in the y equals axis. So that means that for this one, just put my y here, and here is my x-axis. So the domain for this one, again, because it's the inverse, we basically swap the x and the y. So in that case, the range becomes the domain, and the domain becomes the range. So in this case, the domain is from 0 to infinity. The range becomes from minus infinity to infinity. We don't have a horizontal asymptote anymore, but we'll have a vertical asymptote. And in that case, it's going to be the x equals 0. There is no y-intercept, but in the x-intercept, then again, it swaps. So instead of having 0, 1, we'll have 1, 0. Nope, there is, usually it's just exchanging the x and the y to get the inverse. Okay, no, the tricky business is my brain. Okay, so that's important, noticing those points right there. So I had said previously before that I had b to the 0 is equal to 1. So for any base to the 0 is always going to equal 1, then what that means logarithmically, that the log to any base of 1, so again, I'm just switching the x and the y here, is equal to 0. So there's our function. Any function logarithm of b of 1 is going to equal 0. So again, that's a quick question that can be asked on the exam. And so make a note of that. It also doesn't involve a calculator. If you don't believe me, you can always pull one out. Here's a Casio FX991. Let's see, mode. And any number, so we have 6 to the 0. Boom, equals 1. And if I have log of 1, that equals 0. If you don't believe me, there's 6. Log to the 0, log to the 1 is 0. If I put in log to the 0 in there, we should expect an error. The reason for that is because it's not defined for it. So if I push it, boom, math error. It's not like the calculator doesn't know what to do. Well, it doesn't because it's not defined. So we need to know why. If you write, you know, you always see those math memes where they go log of, you know, b of 0, and they'll equal math error. Yeah, it's just not defined, so it's undefined. And again, the reason for that is it's not in our domain. So maybe I'll make a little comment here saying that the limit as x goes to 0 from the right-hand side, so as I'm going to the right-hand side, that's going off to negative infinity. And So again, that's kind of implying that this is a vertical asymptote. And we can also look as x goes to positive infinity to see what kind of behavior it has. And it keeps getting bigger and bigger. So it's equal to infinity, and this is for positive bases. Actually, it's for b greater than 1. Okay. What I'm going to do now is I'm going to open up a spreadsheet, and screen 1, there we go. So I can open up a calc sheet, which is the LibreOffice's version of Excel or a spreadsheet. And what I wanted to do is we'll do just some quick graphs. So I can use x, and I'll use 3 to the x, and then I'll use log to the 3 of x. Let's see, and we'll use some small, we'll work around 3 or maybe 2. Let's use -2. And we can do some quick graphs here. So this would be 3, and we would use this one over here. Gives me a small number. That's starting to look good. Are they going to give me log? Calculates the logarithm to any specific base. Okay. Now I wonder. So okay, there we go. So I need to use the number. So that will be my x, and then I have a base. I believe if you don't specify the base, then it should be automatically goes to 10. So I will pick the number, and then I will also, we'll do our base is 3. Error. Why is there an error? Everyone in the chat should be saying, why? Why is it an error? Why is it an error? B is greater than 1. Yes, because it's, someone wrote it's a negative exponent. Not quite. It's because I've put in a negative value. So I have x equals -2. And remember, remember in this case, the domain is defined from 0 to infinity. So I've actually put in a number that I can't put into that function. Yes, exactly. It's the domain. Yep. So jumping back to that, so like we'll see some. Remember, we just covered that with the error of 0. So this is not possible. So we'll delete that just to kind of clean that up. And what I'll also do is, let's put in a reflection line as well, just to make it work. So x equals y, or y equals x, will give me that straight line, that diagonal line that we'll have. And I will then come over here. I will do a pivot. No, we don't want a pivot table. We want a scatter plot. I want it connected. There we go. Maybe I'll make that a little bigger. We'll finish this. perhaps maybe I won't plot everything up to, we'll kind of get rid of this. Just kind of make that look a little, so we can see it a little better. Yeah, so again, this is our 3x, 3 to the x. Here is our y equals x, and you can see that it is reflected in the, about the y equals x. Now, why am I not getting the asymptote is because I haven't picked values getting closer and closer to 0. So we could do that. We can just kind of go up to like 0.01, 0.0001. And I'm getting in some errors. We'll delete those errors. As well as we probably are starting to run into some calculation. There we go. So probably we're running into some of the some issues in terms of numerical stability about that. So what I can do is go back to how it originally looked. There we go. And what's the other thing too? Okay. So we know, for instance, okay, I know I'll have to use some colors. So we'll use some color pens. Oops. Shoot. There we go. There's my y equals x. There's, okay, so in this case, I can tell you that roughly, if I drew something like this, which is kind of like my x, my 2x, then kind of about an equal distance from there. Something like that. That would give me my log 2 to the x. If I had my x to the 3, that would grow faster than 2 to the x. So there's like, say, 3 to the x. And that would mean that this should grow slower then. So in this case, if I had a larger base for the exponential function, say 2 to the x, I would expect it to be growing slower than, say, 3 to the x. Now, conversely, that if I have to flip it, that if I have log to the base 2, it should be growing a little bit faster than log to the base 3. And if I draw one more, which is, I'll use a red, something like that, 10 to the x, I would also expect this to grow even slower. So there's a log 10 to the x. Okay. So with that, so I've drawn that. Let's just do an example where we sketch. So in this one, we're going to find the domain. Find the domain of f of x, log to the base 10 of x to the minus 3, and sketch the graph. So again, we saw how the domain is important. So we'll actually find what that domain is. So we have the domain. So we know that the domain of the base of this function, kind of our function that we're looking at for the logarithm, and I'm going to call this kind of like the kind of, I can't call it the base function because that'll sound weird because we're talking about the base in particular, but kind of this original function that we're working with, and then we apply a transformation. So we're going to do some sort of shift or compression to get to the function that we need. But I'll call this kind of like the original function. And we know that the domain has to be greater than 0. So we're going to look at all the x's, and again, that means that in the inside here, the domain has to be greater than 0. So it's x minus 3 is greater than 0, which means that x has to be greater than 3. And if I write that in my notation, like my interval notation, that means that it's from 3 to infinity. So what that tells us then is that we're just going to, for this function, there's nothing really else. This just tells us that we're going to be shifting the graph by 3 units. So that means shift by 3 units to the right. And so you don't have to do a really amazing sketch at this point. What you just need to do is, again, draw in our vertical asymptote, which is x equals 3. Another thing that we know is that it has to cross the x-axis at kind of one unit over from that vertical asymptote. So that's it. And there is our sketch. Okay, so why is this kind of important? Is we'll end up using a lot of exponential functions, or we end up using logarithm functions when we're working with some real-world applications. Sometimes we're required to solve for an x. We can have logarithmic questions, or sorry, logarithmic equations. So in this case, we can solve for x. And in this one, we're asked to find the logarithm. So the log to the base 10 of x is equal to 3. Oh, sorry. Can you explain the values of a and b? Oh, sorry, where I'm not sure about what A or B is. We're using B to mean that it's the base. starting to sound like The Price is Right. I don't know if you could hear the honking outside. So I'm not sure what the A and where the A in particular that you're talking about, but the B is what we're usually using for the base. We use, for instance, the logarithm to the base B, or we're using for the exponential function the base B to the x. Okay, so and if you want some more clarification, again, just kind of ask what the A is part. I'm not quite sure. Now we're going to solve for x. In this case, we can use two methods. So the first one that we can do is kind of like just converting it to its equivalent form. So for instance, what I mean is I have a log of 10 to the x equals 3, and I can use my kind of rule that I have up here. So in this case, I have log to the 10 to the x equals y. So for instance, for graphs, I don't think I've ever, there's two cases when we were talking about exponential functions. For instance, we had an exponential function like this, and that would be when b is greater than 1. So this is for the exponential function. Or if I had b was between 0 and 1, then instead I had it flipped like that. So if this was 2 to the x, then if I had something like 1/2 to the x, like that, and actually what you would see is that if you drew those on the same axes, like that, that this 2 to the x is reflected in x equals 0. So these are reflections of each other. So I assume that it's for b greater than 1. I think that's what you mean, that it's kind of positive growth. It's increasing, and if I have it to the 1/2, in this case, it's now decreasing over the entire domain. Okay. Now going back to this, this is one method I can do. I can solve by writing it equivalent. So I have log to the b. So this is 10x equals y. So in this case, my y is 3. So you can think of, there's my base, there's my y. So in this case now, then I want the base. So the 10 to the y, which is 3, is equal to x. Which means then that x is equal to 10 to the 3, or that's equal to 1,000. Now, I always forget, I always get confused about stuff like that. So I'm used to writing it as a second way. So the second way that I usually do it, and you can have a preference for which way you want to do it. But there's the log of 10 to the x is equal to 3. And then what I do is I apply the exponential function to both sides. So I'll raise everything, I'll write this all to the 10. So what I mean then is I'll have 10 to the log of 10 to the x, and that's equal to 10 to the 3. And then I also know that because I've done this, this is an application of I have an inverse function applied to the original function that maps it back to the original element x. So again, that's 10 to the 3, or that's equal to 1,000. Ooh, I have like 3 minutes left. Oh, 2 minutes left. Okay. So this one is solve 10 to the 3 minus 2x equals 4. So what I'm going to do is I have 10 on the side. So what I'm going to do is I'm going to apply the inverse function to that. So I'm going to have log of 10 applied to 10 to the 3 minus 2x equals log to the 10 to the 4. Oh, sorry. Log to the base 10 of 4. And again, going back to our notes, so again, I have my log of base 10 to the 10 to the whatever here. That just makes this equal to 3 minus 2x. Now I can't do any simplification on the right-hand side, so I'll leave it as is. So log 10 of 4. And then I proceed with my rudimentary algebra, which is I'm going to solve for x. So I'll bring this 3 to the right-hand side. I'm left with minus 2x. That's a good question. I will get to that question, Miguel, when I finish that. I'll get to that, yes. And then I'm going to just kind of multiply by minus 1, so that I'll just have 2x equals minus log of 10 plus 3. So I'll have 3 minus log 10, just like that. And I'll get rid of that 2 by dividing it both sides by 2. And so we're done. And so, again, this log 10 isn't very easily calculable. So I will write 3 minus log of 4 divided by 2. Oh, divided by 2. So that's approximately 1.1989. So Miguel asked a question, which was, so note on calculators, usually log means log to the base 10 on calculators. And this is what we usually refer to as common log. But be very careful, because sometimes in economics or in other textbooks, read to make sure that when they write log that they mean 10, because sometimes they might write it using a different number. So for instance, it's not always, so you should check your textbooks, not our textbook in particular, but if you get into higher up economics textbooks, so check your textbook, what they mean. Because sometimes they may define that log is equal to log to the base 10, or sometimes they mean that log is equal to log to the base 2.718 ... which is a transcendental number, which we call e, but that's something that we'll get to in the next lecture. Now, since we're on the topic of calculators, I know that it's 5:31, but what we can do is I'll show you one simple trick if you're working on some of your exercises, if you are working on stuff like this, something called change of log. So if you have you're working with a calculator like this, and I have log to the base b of x, and you only have your calculator, and you're like, oh, I don't have the logarithm to the base b. To change the base, it's the logarithm of x, so in this case it could be like 10, so log of 10 to the of x, divided by log of 10 to the base b. So if I had log of 3 and 4, that's log of 4 over log of 3. And that is equivalent to log of 4 divided by log of 3 is approximately equal to 1.2619. Okay? If there's any other questions, feel free to send me an email. I don't want to keep you past our lecture time. And again, our lecture starts at 3:40 tomorrow. There is no quiz because we'll have a test on Thursday. So the test will be on everything from test 2 up until what we covered last. I think you mean test 1. So the test will be everything from test 1 up to what we covered on last Thursday. Yep, up to the last assignment that I had posted. Okay. Well, thank you for everyone tuning in on this Monday afternoon. I will see you tomorrow. Take care.